Okay, now I want to consider sketching y equals a tangent of bx, and I'm going to limit myself to just one period of the functions, because if we know what's going on for one period of the function, we know what's going on in general. Another thing is I'm going to think about specific instances or examples of what this a does and what this b does. So we're going to start with our tangent function. Okay, we have y equals the tangent of x, and this period is pi. So 1/4 of the period is pi over 4. And this essentially tells me where I want to have my tick marks to be pi over 4 apart. So I'm going to have something like this. And so here's my y-axis, my x-axis, pi over 4 apart. So I'm going to have, here's going to be 0, pi over 4, then pi over 2. Then I have a negative pi over 4, negative pi over 2. So these 5 points on the x-axis, we want to think what's going on with them for our y's. So first of all, we have these asymptotes here, right? At the extremes, and I know that my tangent of 0 is 0. If pi over 4, we're going to up here at 1. Negative pi over 4, we're down here at negative 1. And we have these asymptotes. So my tangent function is going to look sort of like this. And this would be my y equals the tangent of x, one period of it. Or I might think, what happens if I double this? What if I have y equals 2 tangent of x? My origin stays my origin. I'm doubling all the y values. So instead of being at 1 here at pi over 4, I'm going to be up here at 2. And instead of being at negative 1 here at negative pi over 4, I'm going to be down at negative 2. I still have these asymptotes. I'm still going through here. So I'm going to have something sort of like that. I'm just stretching vertically by this factor of 2. On the other hand, what if I have y equals, say, 1/3 tangent of x? Well, still at 0 I'm going to get 0, but now instead of being at 1 here, I'm going to be at a third. And instead of being at negative 1 here, I have to estimate I want to be at negative a third. So I don't want that. And so my graph is going to look something like that. So basically, the thing that A does, if A is positive, we're stretching our graph or shrinking the graph depending on if we're bigger than 1 or less than 1. The 2 here is stretching the graph vertically by factor 2. The 1/3 is uh, shrinking the graph by a factor 1/3. So now consider, what if A is negative? What happens on one period of this? So just in general, if I negate a function, I'm going to be flipping about the x-axis because my y values switch when you negate them, right? So here's my tangent function is like so, right? This is y equals tangent of x. For the negative of the tangent, I'm going to be, so instead of pi over 4, I'm going to be doing this. So you have to use your imagination a little bit. But you see how these points work, because here at pi over 4 I'd have 1. This is y equals negative tangent of x. Instead of at 1 I'd have negative 1. So I would have a point here. And instead of negative 1 here, I'd have a point 1 here. So I'm still going through the origin. I'm going to have these asymptotes on the end points. of this interval from, what is this, negative pi over 2 to positive pi over 2, right? This is pi over 4, and then this was pi over 4 like so. So it's going to be decreasing. The slope here is going to be negative 1. It's not leveling out. It's going at this pace here. And then if I do want, I can do things like, what if y equals negative 2 tangent of x? Okay, so for this one, I could write the tangent and negate, or I can multiply this by 2. I'm going to have something like this now. Okay, so I can think of this twofold to get the blue graph here. Is one is I negate the function tangent, so that flips it about the x-axis, and then I stretch by a factor of 2. And that's how A is going to affect these things. Okay, now we want to consider what happens on the capital B here with respect to this tangent function. So I want to consider a couple of examples, and we're going to do these for one period of the function, because once you know what's going on for one period, it being periodic, you know what's going on for the rest of the number line by repetition. So I'm considering y equals, say, tangent of 1/2 x. Okay. In general, my period is going to be a pi over b here. So I have pi over 1/2 is 2 pi. You might notice that the period of tangent was pi, period of a half x is 2 pi, tangent of a half x is 2 pi. Essentially my x values have to be twice as large to compensate for the 1/2 here. And then I want my 1/4 of my period should be then 2 pi over 4 is pi over 2. And so I'm going to have my points of interest here, right? So I'm going to have, here's 0, pi over 2, pi, it's negative pi over 2, negative pi. And what you might notice here is on these extrema, we're going to be in trouble at pi and negative pi, because tangent, if I put pi into my tangent function up here, right, then I'm in trouble because the tangent of pi over 2 is undefined, and near it we have vertical asymptotes. So here would be 1, here would be negative 1. So I have something like this. I'm going through the origin here. I have these points. And so this is my graph of one period of that function. Okay, now we'll consider another example of y equals a tangent bx. The b, so I want to consider y equals the tangent of 3x. So I know that my period is pi over b here is going to be a pi over 3. So 1/4 of the period is going to be pi over 12, right? You multiply pi over 3 by a quarter, you have that. So this is going to look like the other ones we just did, but these are shrunk in a little bit. So now I have pretty much my same graph, but I have 0, pi over 12, 2 pi over 12 is pi over 6, negative pi over 12, negative pi over 6. And you can think about plotting points, but essentially I have the same exact behavior here as before. And here's 1, down here's -1, going through here, here, those 3 points, and then these asymptotes. So this is what my graph looks like, okay? And it's shrunken in here. So, except for the scaling, they're all pretty much the same. Okay, so in summary, if I have y equals the tangent of bx, where b is bigger than 0, I can get its graph by graphing the tangent of x and stretching or shrinking horizontally. So you can think about what this looks like. Okay, so maybe I'll first draw my tangent function like so. So this is going to be y equals tangent of x. Okay, and then I want my tangent of a half x. I'm going to double all my x coordinates, so I have to sort of think about doubling those guys, right? So this would be y equals tangent 1/2 x. And then for y equals tangent of 3x, I'm going to have a third of these values. Okay. So I haven't drawn the asymptotes because it'll clutter up the screen, but basically you see how my x values are. And another thing is that, of course, this is just one period. Your actual graph, you're going to have, period after period here. So we would have on all these guys, right? We would have our asymptotes, right? Equally spaced here. And so we're going to have something like this, right? Something like this, etc. So that's my graph of the whole thing, right? Okay, now I want to do an example of graphing a tangent bx minus c. So for instance, I have y equals 2 tangent of 3x minus pi over 2. So I recall what the graph of y equals 2 tangent of 3x was, right? The period was pi over 3, right? Pi over b. So 1/4 of the period is pi over 12. And that's going to be true even if I have this pi over 2 here, right? For this family of functions. So the period is going to stay pi over 3. And what we're going to do is move this to the left or right depending on these constants here. So remember our graph here, we have our tick marks at, here's pi over 12, negative pi over 12, here's 2 pi over 12, negative 2 pi over 12. So I haven't really simplified those tick marks where they're at here, because I'm going to think about this. And so here might be 3 pi over 12, and maybe here's 4 pi over 12. All of those reduce, right? But for graphing purposes and for the purpose of this example, we'd want to do this. And then how about this 2 here? Remember, this is going to be up here, we're going to be at 2. And down here, we're going to be at negative 2. Right, so we've done all this before. Okay, so now we want to think about in this graph. So the question is, how does the graph of, let's say, y equals f of 3x minus pi over 2 relate to the graph of just y equals f of x? I mean, I can do this in general. I can do this for this function here. Well, basically what we have to do here is take this 3 out. So my f of 3x minus pi over 2 is going to be f of 3x minus pi over 6. So I divided pi over 2 by 3 to get pi over 6 here. So I could do that in general. If I had numbers other than 3, I could do the same sort of thing here to get this. And so the 3 here, this is going to shrink our graph horizontally by a factor 1/3. So you shrink horizontally by a factor 1/3. And here, when I replace x by x minus pi over 6, we shift the graph to the right pi over 6 units. And for this graph up here, it's 2 tick marks. But I don't have to have this exactly at tick marks. If I had 5 here, for instance, I would write things in terms of decimals. I would just shift over 5 units. So you don't want to overgeneralize on that. So now, I'm going to go back up to my graph here. I want to shift it to the right to tick marks. So what happens on my asymptotes? Well, here's this 2 pi over 12 over 2. I'm going to be right here. Right? So I can move my asymptotes here. What about this point here? It's going to move over to here. This point here is going to be here. This point here now is going to be here. My left asymptote is going to be the y-axis, so I have something like that. I've shifted all my units over pi over 2. Well, pi over 6 to the right. Okay, now I want to use my calculator to sketch this function y equals 3 tangent of 1/2 x. And I would try 83, but this whole same things will work on 84, 83 plus, 84 plus. And basically, because it's tangent, my period here is, we might recall, it's pi over b. So I have a pi over 1/2. So here I get 2 pi. So 1/4 of my period is 2 pi over 4 is pi over 2. And let's see, pi divided by 2 is about 1.570796327. So because a quarter of the period is pi over 2, that's going to tell me my tick mark. So I'll type this function in here. I have 3 times the tangent of 1 divided by 2 times x. And I need the right window. So if the period is 2 pi, I might go from 2 periods would be from negative 2 pi to positive 2 pi. So go negative 2 times pi to 2 times pi. My scale now, my scale here, I'm going to have it to be my pi over 2, which again was part of the 1/4 of the period. And I'll leave my y's as they are for now. And I'll graph and see what I have, see what I got here. Okay. And so you can see this is a good looking graph. The one period, you know how we did in the section where we just graphed one period. The center of this is one period, and then off to the left I'm going to have another period, off to the right periods, and so forth. It's going through the origin. The vertical asymptote, one vertical asymptote is at, remember this tick mark's at pi over 2, so this is pi, right? X equals pi is going to give us a vertical asymptote here. Notice as well that, if you put pi into tangent of 1/2 x, you get tangent of pi over 2, which doesn't exist. So you could think of it that way as well. What about this 3 here? We're just eyeballing this at pi over 2. Looks like I'm roughly at 3. I could trace and see. I guess what I could do is I could just calculate it and see if I have, let's say I put y equals 3 here and graph this. That's y equals 3. And then I can do, so I can calculate the intersection. So my first curve, second curve, and then I guess. And so when y is 3, I have this 1.5707963, which is what I had over here roughly. So I know this is the right graph. And then this repeats over and over. So clear this. Oops. So this is going to repeat over and over. If I want, I can do that. So I have 3 times tangent of 1 divided by 2 times x, and maybe I want to graph this. Well, I just graphed this, but I wanted to change my window here and say, what if I go from, say, negative 20 to 20 on my x's? Then you can see that we have all these periods of this tangent function there going on.